Hi guys! So in geometry today we're going to talk about the connection between parallel lines and congruent angles and how you can use those in a proof. First of all, just to give you a little background, you've probably been talking about how if you have parallel lines with a transversal, then you end up with pairs of angles that are congruent. Now my little trick that's kind of quick and easy is every acute angle here and down here, they're all congruent to each other. And every obtuse looking angle, like this one, that, and that, those are all congruent to each other. And there's names for the different pairs. The two pairs of angles that you use the most in proofs is alternate interior, which that would be like that one and that one. And then you also use same side interior, which would be like that one and that one. Another word for same side interior is consecutive interior. So the alternate interior pairs, those are all congruent. But then if you're doing same side interior in a certain proof, those are going to add up to 180. And another one that I just remembered that you use a lot in the proofs is corresponding angles. Like for example, if you have this angle and then this angle down here, those are corresponding. Those are another pair that are congruent. So corresponding are also congruent. Alright, so now for our proof. In our particular proof, let's write our givens down. We have AB congruent to CD. And then we also have BC congruent to AD. So we'll mark that in our picture. Those are both given. Given. Okay, so now AB is congruent to CD and BC congruent to AD. Now just like a lot of the proofs you've been doing, getting triangles congruent is a key thing that most of them will still involve. So I can see in my two triangles here that if I say that BD is congruent to itself, I'll have that, and I can say BD is congruent to BD, and that's by reflexive. And by saying that, I have my two triangles congruent because of SSS. So there's one of them, and here's the other. It's pretty obvious in this picture. There's no overlapping triangles or anything. So we can say that triangle, let's call it BCD, is congruent to triangle DAB. Get those letters in the right order. I usually just follow along the congruent markings, like BC was the double marking first, and then down to D was the single marking. So I called it BCD. So in the other triangle, I call it DA, because that follows that first, and then B, because it follows that. Alright, so let's get rid of these markings here. Alright, so now that was by SSS, which is just all contained in steps 1, 2, and 3. Now, we are trying to get AB are parallel to CD. Now, the only way to get those parallel is by using a correct pair of congruent angles. So if I want AB to be parallel to CD, one pair of angles I could use would be this angle congruent to this angle, because in relationship to those two lines, those are alternate interior angles. And if alternate interior angles are congruent, then the lines are parallel. So let me just get rid of a little bit of this highlighting, and I'll show you. So this angle traces out that line and that transversal, and then when we get over here, the other angle that I marked traces out that line. So you see that Z shape? That's a key feature of the alternate interior angles. You get those Z shapes all the time. So now I'm going to say that angle ABD is congruent to angle CDB. And that's just because the triangles are congruent. So that's by CPCTC. And then in my final step, I can say the proof statement that AB is parallel to CD. And that's because those angles that I just mentioned in step 5, these ones here, those are the alternate interior angles. So I can say if alternate, I'm just going to abbreviate, interior angles are congruent, if that's true, then lines are parallel. And that's the end of that proof. Now you can also say these different reasons in reverse. Like this reason I just wrote down, the if and then can just be completely switched, which is what we're going to do in our next proof. I can say if lines are parallel, then alternate interior angles are congruent. So let's switch over to this other proof and take a look at what it's telling us. So we have given that O is a circle, and also given that NR is parallel, so I'll put the little parallel arrows. It's parallel to PS, and that's all that's given, and we're trying to prove the triangle OSP is isosceles. So let's just copy down our givens. NR is parallel to PS. 1 and 2 are both given. Given. All right, now OSP, we're trying to prove that this big triangle is isosceles. Now let's think about that. One way to prove an isosceles triangle is if you have congruent sides, but since we're working with parallel lines, more likely we're going to have congruent angles. So if we could get angle P congruent to angle S, we would be all set, because then we could say our proof statement about OSP being isosceles. So that is our goal. So now let's work forwards by what they gave us. So since NR is parallel to PS, so NR is parallel to PS, let's pick a pair of angles that really is congruent. I could say, and let me just get rid of these arrows so they're not in our way. I could say that angle P is congruent to this angle right here. And that's because they're corresponding angles that are touching those two parallel lines. So I need to say angle P is congruent, and I have to use 3 letters for the other angle. So angle ONR. And that's because if lines are parallel, then, and those are corresponding angles, so then corresponding angles are congruent. Okay, then if I go to the other side of the triangle, I can say the exact same thing. I can say angle S is congruent to angle ORN. So for step 4, I'll list that. Angle S is congruent to angle ORN. And that's just the same reason as 3, so I'm just going to be a little bit lazy and write same as 3. It's a little bit shorter. All right, so now we somehow have to get angle P and S congruent to each other. Well, the next key step is the part about the circle. They said O is a circle, so that means that radii are congruent. And this ON and that OR are radii of the circle. So I could say in step 5 that ON is congruent to OR, and that's because all radii are congruent. So I'll just abbreviate that. All radii are congruent. Usually when they tell you about a circle, that is what you need to be looking for. Look for congruent radii, because that is the main reason they put shapes into a circle in the first place. Now the nice thing is, since I know those two sides are congruent, that makes this little tiny triangle isosceles. So now angle N, this one here, and angle R are congruent to each other. I have to use 3 letters to describe that. So I'll say angle ONR is congruent to angle ORN, and that's because this is the shorthand that most people use. If sides of a triangle are congruent, then the angles are congruent, and you can usually just write the reason like that. Now that those angles are congruent, our angles that we really wanted to be congruent will be, and it's because of the transitive property. Because if I list it in order, I'll write it down here. I said angle P was congruent to angle ONR. I said that earlier in the proof. Then I just said that angle ONR is congruent to angle ORN. That was in step 6. And also earlier in the proof, I said that ORN was congruent to angle S. So I have this big long chain of congruences, so I can say angle P is congruent to angle S in step 7. Angle P is congruent to angle S. And that property is transitive property. So that's transitive. And that's what we wanted all along, because now that makes triangle OSP isosceles. Some teachers make you say that the sides are congruent first, so I'll do that just in case. We can list that OP is congruent to OS, and that's just because we had the angles congruent, so you can write that one step backwards. If angles, then sides, and then this is our final step, that triangle OSP is isosceles. And you could, most teachers let you just say definition of isosceles. It's because we have a triangle now with 2 congruent sides, and that's what an isosceles triangle is. And so that should be the final step for that proof.